Welcome back to Cybernetlearners. Rocket, this is episode 4.2 of our Android Pentesting Mastery Series. In this episode, we will explore Android security architecture and how applications run securely on Android devices. If you're new here, consider subscribing to stay updated with the latest in mobile security and ethical hacking. Now, let's get started. Let's talk now about the Android security architecture and how we actually have applications run on Android phones securely. So one thing to keep in mind about Android is that everything is based on a Linux operating system. So this means that if we have a command line interface into our Android phone, it can actually take commands just like any Linux device. So you have your basic commands like ls for listing the file system, cd to change directories, rm to remove files, etc. If you're not familiar with the Linux basics, I would definitely recommend that you get a TryHackMe account and do their Linux basics room, because that will definitely get you up to speed on how you can do some basic Linux commands. We will be using that throughout the course because we can actually get a shell into our Android phone. We'll be able to run Linux commands on our Android phone. So definitely, if you don't know anything about Linux, I recommend going out there and learning something before you go further in this course. So something to keep in mind about Android being based on the Linux operating system is that the permissions to folders and applications are going to be dependent on the Linux file permissions model. Maybe you are familiar with this, where you have 10 different digits that determine permissions for files in the Linux operating system. The first digit is the file type, which can be a directory D or an executable file, X. The next set of digits defines the owner's permissions, as shown in the picture. For example, the owner has read and write permissions, which is indicated by our W. The next group of permissions is for the actual group, and in this case, it only has R for read. The final set of 3 is for other users' permissions, which is also read-only, R. The important part about this is that our applications are actually isolated from each other using this file permission model. So you're going to want to keep this in mind when we talk about how this actually affects real applications on an Android phone. Android runtime and application isolation. Now, every application on an Android emulator or physical Android phone runs inside a virtual machine known as the Android runtime, ART. You may hear the term Dalvik Virtual Machine, which was the original runtime for Android. Sometimes, people still refer to Dalvik bytecode when talking about decompiling an application into its source code and machine code. However, Dalvik VM is no longer used in modern Android versions. Instead, it has been replaced by Android Runtime, ART. The Android Runtime, ART, is a modern translation layer that converts an application's bytecode into device instructions. Every application runs in its own sandbox virtual machine, meaning each app is assigned its own folder. Each app has its own owner, UID. Apps are sandboxed from each other by default. Application storage and UID assignment. On an Android device, each application is assigned a unique user account. This is what it looks like from an identity and access management perspective. Each application gets its own user. The user owns the app directory. The user ID, UID, is assigned between 10,900 and 99,999. For example, a UID 10188 might be assigned as U0_188. Here are some examples of app storage directories. /data/app/com.example app general app data storage. /data/data/com.example.app runtime storage. /mnt/card/android/data/com, that example that app external storage. Each application is isolated, and different apps have separate directories. For example, com, that example that app has its own directory. Com, that example 2 to app has a totally separate directory. They cannot access each other's files unless explicit permissions are granted. Inter-app communication and security mechanisms. Applications can only share data securely using. Content providers use to share structured data. Broadcast receivers use to receive and process system-wide events. For example, when you open a link in Chrome or Firefox, the browser uses a broadcast receiver to handle the request. Additionally, Android enforces digital signatures to ensure apps haven't been tampered with. Root access and emulators. By default, Android restricts root access to prevent unauthorized system control. However, for pen testing purposes, we use rooted emulators to gain access to application data. In this course, we will set up rooted emulators that allow access to system files, application directories, hidden storage locations. An important note, emulators with Google Play APIs do not allow root access. Emulators without Google Play APIs allow full root access. We will cover this in detail in the emulator setup video. Android profiles and user management. Android also has a profile management system, which enables work profiles and personal profiles, separate clipboard contacts, and storage access. BYOD, bring your own device security features. For example, if you have Microsoft Teams installed on a work profile, the clipboard will be separate from your personal profile, preventing data leakage. Another key feature is the primary user, which is created when the phone is first set up, always running in the background, can only be removed via factory reset. Android also supports secondary users, which can be added manually but are controlled by the primary user. And likewise, you can also have guest users. So you can have a guest user on your device, a fast way to give someone access to your phone, and maybe limit what they have access to. Obviously, when we're talking about device security, something important for a lot of parents out there is things like kids mode, right? To isolate what kids are allowed to get access to. Things like Google Kid Spaces, which is currently only available on tablets, but I'm sure it will be supporting additional Android devices in the future. You can also set up profiles for kids and use vendor-specific kid modes, such as Samsung Kid Mode. There are also some applications out there that gain full access to the device to allow only certain websites for kids or to have a time-limited usage of certain applications. Things like NetNanny and Norton Kid can be useful applications for parents looking for kid mode features. Now moving into the Android architecture, and this is where we're going to get into the real depths of all the different aspects of Android. We're going to do this based on this diagram taken from the Mobile Pen Testing Git book. We'll start from the bottom with the Linux kernel, move up to the hardware abstraction layer, go into the libraries, which come in two different varieties, native C or the Android runtime. Then we'll go to the Java API framework, and finally finish up with the system apps. Okay, so obviously Android is based on the Linux kernel, and back in November of 2012, Security Enhanced Linux, or SE Linux, was introduced. If you don't know anything about SE Linux, I definitely recommend reading up about it. It was not enabled by default until July 2013 with API Level 18, so something to consider when looking at previous versions of Android. You can see that the Android runtime was now used by default in November of 2014, and obviously, tons of improvements have been made to Android over time. Just some interesting versions of Android to know about. As you can tell from this picture, depending on which version of the Android operating system our application supports, it can actually determine some of the security vulnerabilities we might find. A common attack path we'll use throughout this course is running our application on API level 29 and maybe on API level 22 as well, to see the differences in security and to check if the application behaves differently depending on the API version. Something important to keep in mind when it comes to the Linux kernel is that Android devices must support multiple CPU architectures, such as ARM system-on-chip, 32-bit, and 64-bit chips. Applications are explicitly told which version of the Android runtime to run on. So in our Android manifest.xml, when we get to static analysis, we'll talk about the MinSDK version. This determines what versions of the Android API or operating system our application can run on. From a security perspective, as seen in the Linux kernel picture, the higher the API version, the better, since we're building on the experience of the Android operating system. But developers always want to include as many customers as possible. If an application could run on, say, Android runtime version 1 up to the most recent version, it would include 100% of the marketplace. However, the downside is that lower versions of the Android operating system can have more security vulnerabilities, allowing for different types of attacks. We need to be careful about which versions of the operating system our application is allowed to run on to balance security and reachability. The Linux kernel also allows access to the physical components of the device controlled by drivers. Just like any device, Android devices have drivers for different hardware components. This is where the hardware abstraction layer comes in. The hardware abstraction layer allows applications to access hardware components irrespective of the device manufacturer or type. Imagine two different Android phones by two different manufacturers in a store side by side. They may have different internal components, like a camera made by one company or a Bluetooth sensor made by another. But the hardware abstraction layer allows applications to access these components generically, like accessing the camera, microphone, location, Bluetooth, or touch drivers without knowing specific manufacturers. Some interesting and emerging hardware abstraction types include automotive. Many phones now support Android Auto and Apple CarPlay, meaning our phone interacts with our vehicles. IoT. Devices like fitness watches, Pelotons, and smart home devices like Alexa and Google Home interact with our phones. Gaming peripherals. Some phones can be connected via USB-C to function as a computer with controllers and other gaming accessories. Now, let's talk about native C versus the Android runtime. C and C++ are the device's native languages, and anything running through them does not require going through a virtual machine. For example, the WebKit built-in web browser for apps, OpenMaxAL, and OpenGLES, UI frameworks for displaying 2D and 3D models, run natively. Java, however, is often easy to code in, so many developers prefer it. Anything written in Java runs through the Android runtime environment. Older apps are usually built in strictly Java, while newer ones use Kotlin. In 2019, Google announced that Kotlin is a preferred coding standard for Android applications, and currently, 60% of professionally developed applications use it. For more about Kotlin, visit developer.android.com/Kotlin. Now, moving into Java API framework. This is what allows your app to interact with other applications and the device itself. In the Java API framework, we have content providers, a way to share data with other apps using a specific directory format like content, / application URI / directory. View system, used to make the app's UI and normalize it across the phone. Managers, handle background processes like notifications, telephony, and package management. Package management is crucial for checking app updates and ensuring integrity. Location manager, retrieves fine and coarse location data for apps that need location services. Finally, the last layer of the Android architecture, the system applications layer. This is where you'll find pre-installed apps like contacts, phone, system settings, text messaging, and camera. Many Android devices come with default Google applications pre-installed, like Gmail, Google Maps, and Google Settings. Vendors like Samsung also include their own vendor-specific pre-installed apps. One of Android's key advantages is its customizability. You can always set up new default apps to replace vendor-supplied or system applications. Just go into the settings and change default apps if you prefer something else. Okay, that wraps up our discussion on Android architecture. Stay tuned for the next episode, where we explore practical pen testing techniques. If you found this video helpful, don't forget to like, share, and subscribe to Cybernetlearners. Stay ethical, stay secure, and see you in the next video.